Okay, so this question is all about the ideal gas equation. I'm going to go through both of the approaches that it says there are to solve this. Okay, so the first one says that you can work out the moles of gas using the ideal gas equation and put back into the equation with the new conditions. Okay, before we do that, I'm just going to remind you about the ideal gas equation. So that's PV equals nRT, and N is the number of moles, R is the ideal gas constant, which is 8.31. T is the temperature, we've got to remember that's in Kelvin. P is the pressure measured in pascals, and then V is the volume, which needs to be in cubic meters in the ideal gas equation. And that is going to be a problem in this question actually, because we've got cubic centimeters and we've got cubic decimeters. Okay, the actual key to solving this with solution number one is knowing this bit of information that I've got here, which is that 1 mole of an ideal gas occupies 22.4 cubic decimeters at standard temperature and pressure. That's 298 Kelvin and 100 kilopascals. So that bit of information is in the spec, so you need to know that, and that's something that you need to bring to questions, in particular ones like this. So the first thing to do then is, if we know we've got 40 cubic centimeters of oxygen, 60 cubic centimeters of CO2, that gives us a total of 100 cubic centimeters. We can use that bit of information about the molar volume that an ideal gas occupies to work out how many moles we've got in that 100 cubic centimeters. Okay, so we're going to do that. So we're going to work out how many moles that 100 cubic centimeters is. And to do that, first of all, we need to get the units the same. So 100 cubic centimeters is equal to a tenth of a cubic decimeter, so that's 0.1 cubic decimeters. So remember, a cubic decimeter is the same as 1,000 cubic centimeters. Okay, so we just scale that up. So 0.1 cubic decimeters divided by 22.4 gets us a small number of moles of gas, 4.46, etc., times 10 to the minus 3 moles of gas. Once we know that, we can then just use the ideal gas equation, PV equals nRT, rearrange it to get pressure, so pressure equals nRT divided by volume, put all of the information in, so the number of moles that we calculated, the ideal gas constant 8.31, the temperature 298 Kelvin, and then the new volume of the container that the gases were put into. So that was given to us back up at the top of the question as 0.50 cubic decimeters, and we need to convert that to cubic meters, so that's 5 times 10 to the minus 4 cubic meters. Once we do that, you will get a final answer, ignore that bit, of 22,110.557 pascals, and the solution in the question is rounded that to 20,000 pascals. Okay, so that's what solution number one was talking about. Solution number two was saying, well, you can use the ideal gas equation and kind of double it up. So what it's really saying there is that in the first situation, the carbon dioxide, let me just start again, PV equals nRT. So the carbon dioxide and oxygen, to start with, are following the rules of this equation. So if I rearrange that just to get PV divided by T equals N and R, where N is constant and N is the number of moles of oxygen and CO2. Now what they're saying in the question is, because the number of moles of oxygen and CO2 remains the same in both containers, that actually this N and R is one big constant. Okay, so what they're saying is, before the carbon dioxide and oxygen go into the container in situation number one, that's going to equal a constant. Oops, I can spell that properly. And in situation number two, in this container, that because the number of moles hasn't changed, the pressure, volume and temperature, pressure times volume divided by temperature, is also going to equal the same amount, that same constant. So all that they've done in the solution is say, well, these two things actually equal each other. And then they've rearranged it to say that I want to work out that pressure. So they've rearranged all of that, and they've got the new pressure worked out, which they've got as 20,000 pascals. Okay, I hope that's helped, and I'm going to leave that video there. Okay, bye bye.